A bridge could be anything as basic as a ladder laying across a lake or as advanced as the Sydney Harbour Bridge. There are 6 types of bridges, including beam, truss, arch, cantilever, suspension, and cable stayed. A beam bridge is the most basic and common bridge used in today's society. Although of the simple perception of beam bridges, they can also be very effective. A large quantity of highway bridges is considered under this category, constructed from I-beams and reinforced concrete. A truss shape is seen when looking at part of a truss bridge's sides, hence the name. The objective of a truss is to assist a bridge in supporting a load from anywhere along the length of a bridge. A truss bridge is a bridge whose load-bearing superstructure is composed of a truss, a structure of connected elements usually forming triangular units. Arch bridges are elegant but are very effective. In regards to effectiveness, it has a restricted range, meaning that their length sizing is greatly limited. Its semicircular structure stylishly dispenses compression through the whole structure and moves weight onto its 2 main abutments that take on direct pressure. A cantilever bridge supports its load with a counter at one end. An issue with using cantilever, also including cable-stayed and suspension-type bridges, is due to the fact that they have to be anchored down to something. Suspension bridges to this day are the most elegant structures perceived by mankind. Their beautiful curved cables are not only stunning to look at, but they allow engineers to design much longer spans than all other types of bridges, except for cable-stayed. Cable-stayed bridges are very alike in reception to suspension bridges, and hence are occasionally lumped together with them. Cable-stayed bridges use its towers as the central point, with cables spinning down to the surface on each of their sides in straight lines. The cables on this bridge are also very taut, unlike a suspension bridge, where there is less tension. For the tested bridge, a Waddell Type A truss was chosen, but this failed instantly due to it collapsing under light load. A Warren truss was then chosen because it uses equilateral triangles to disperse out the loads on the bridge, reducing the forces to only compression and tension, in which the forces in the middle would be more so tension.
Using the concept of square hollow sections, the failure weight for this bridge was 2.5 kilos. The intended target was not met, and further research and development was carried out in order to reach 50 kilos, or the equivalent of 0.5 kilonewtons. Further research led to the discovery of various American civil and structural engineering universities recommending Warren and Pratt truss designs. The Warren truss used equilateral triangles to carry out and spread loads along the bridge. With the decision, we had created numerous sketches of Warren truss designs. Once the drawings were completed, load calculations were performed on both designs to allow us to gain a further understanding on which bridge will fit the brief. The outcome which calculations provided was decided that the Warren Truss Bridge with 3 triangles would be the final design. With the design of the bridge finalised, we constructed and tested 2 types of beams, which were square hollow sections and I-beams. The square hollow sections were 7 by 7 mm and a thickness of 2 mm. The I-beam had a flange width of 5 mm, web length of 4 mm, beam height of 8 mm, and web thickness with a taper design from 4 to 2 mm. To decide which beam would be ideal and be able to handle the great amount of force, we performed a snap test to determine how much force is needed for each beam to fail. The I-beam was 2 times harder to snap than the hollow section. Due to the 450 mm span, the bottom I-beam had a flange width of 9 mm, web length of 10 mm, beam height of 15 mm, and a web thickness with a taper design from 7 to 2 mm. The first step of the bridge construction was to assemble and create the I-beam structural members for the bridge with a configuration of 3-2-1-2-3. The process for constructing the I-beam began with placing 3 pieces of spaghetti next to each other and using super glue to bond the material together. Next part of the process is to place 2 pieces of spaghetti in the grooves between one piece of the 3. 1 piece of spaghetti is placed in the groove between the 2. This creates a pyramid-like structure, which then requires another 3-2 piece to be placed on top to imitate a structural I-beam. The I-beam for the bottom chord had a configuration of 5-4-3-2-1-2-3-4-5. The bottom chord of the bridge was the most challenging, as the spaghetti needed to be joined together to reach 450 mm. To lengthen the bottom beam, we overlapped each piece of spaghetti to reach 450 mm and a width of 5 pieces equivalent to 9 mm. The process from which member 1 was followed and completed. Once the structural members were constructed, we began to assemble the bridge. We created a template with a 60-degree angle to ensure the angles were correct. To cut the members required to the appropriate angles and lengths, we used an angle grinder.
Truss and a waterway truss. Once we had chosen the final 2 bridge designs to construct, we then had to determine the specifics of each bridge and how we would be able to maximize the load carrying capacity. As a bridge would be suspended over a 450 mm gap, we had to ensure that the final bridge we constructed would be adequate. As a group, we estimated that the load carrying capacity for our bridge would be 0.05 of a kilonewton. The reason for this number was because we thought it was adequate and reasonable. With the guidelines that had been set out, we had to adapt new methods to ensure that all requirements were set. We chose size 3 spaghetti and Shelley's quick glue. Firstly, we had to determine what member would be under compression and what member would be under tension. Before we were able to complete this part, however, we had to determine where the support reactions were and where the forces were being applied. In this case, the pulling arm would be from the middle of the bridge, therefore both forces would be applied either side. All of these calculations were conducted manually. However, there were some that weren't. Wind and water were conducted on the computer through SpaceGas. The software we used was SpaceGas. Along with determining the loads applied to the bridge, we would also be able to determine which bridge would hold the greater load. SpaceGas also enabled us to check our calculations. Another key factor that helped produce the optimal bridge when using SpaceGas was being able to see the three-dimensional model before we constructed the bridge. For the small scales and construction testing of the first bridge, the Waterway Truss bridge, we put the bridge over the gap, then connected a bucket of water and added 500 mils of water at a time. The bridge ended up collapsing at 2.5 litres. We decided that the best design would be the Warren Truss. We conducted a strength and snap test to determine the strength. We constructed two structural members, one a square hollow section and the one an I-beam section. After the strength test, our group determined that the I section has the greatest amount of strength. Each member of the bridge would now be made or consisted of an I section with the configuration 3-2-1. However, with the bottom two beams, it would be a configuration of 5-4-3-2-1, as these two beams are the most important members of the bridge. Our final bridge came in at 190 grams, which is 10 grams under what the guidelines were set at. It also carried 0.27 kilonewtons or 27 kilos. This was an amazing effort and ranked as one of the highest in the class. However, we did not reach our intended target of 0.05 kilonewtons or 50 kilos.
Structural testing is a vital part of the construction industry and revolves around showing materials or individual components will not fail when are fit for purpose. Some of the common tests performed include reinforcement bar tensile, compressive, flexural, and buckling tests. The first test is the cylinder compressive test on concrete. Concrete can be designed to provide a vast range of mechanical and durability properties that aid in meeting the requirements of the desired structure. Concrete is mixed at 1 part cement, 3 part sand, and 3 part aggregate ratio. It is then placed in cylinders. The load rate for the testing is 20 megapascals per minute, and after being placed in the mould, samples are cured for 28 days at a temperature of 23 degrees Celsius. And the results from the test are used to determine whether the mixture of concrete meets the required specified strength. Flexural strength is defined as the maximum stress at the outermost fibre on either compression or tension side of the specimen. In this test, the material is placed over two supports with a force being applied in the middle and at the top of the material. The main reason for completing this type of testing is three fundamental stresses are present. They include shear, compression, and tensile. Two tests were conducted, the first being on the larger surface of the 90 by 35 mm timber. This test showed that the larger surface area withheld less load and failed at 5 kilonewtons of force. Next, the timber was tested on the 35 mm edge and was able to withstand 10 kilonewtons of force before it failed. The buckling test subjects the structure to a compressive stress and is characterized by the sideways bend of a structural member. During the test, a load is applied to the top of the member and is increased. It will become large enough which causes the member to become unstable and buckle. The load applied to the timber midway through the buckling test was 69.2 kilonewtons. Software and technology were used to add stress to the member, allowing for more controlled testing environment and precise results. The final test that was conducted was a flexural test of a reinforced concrete beam. Combining concrete with reinforced steel allows the structures to withstand an increased load and gives it more strength. The flexural beam on a simple support will undergo shear stress and bending stress. After further investigation, it was found that steel reinforcement bars are placed at the bottom of the beam to resist tensile force, while the concrete will resist the compressive forces on the top of the beam. Steel has a high tensile strength and is used on the bottom of the beam to counteract the low ductility and tensile strength of the concrete.